Jeffrey Manufacturing Company, mining locomotive, Edison storage battery equipment. Westinghouse, Baldwin, mining locomotive, Edison storage battery equipment. Letter number 2, analysis of the Edison storage battery. The most unsatisfactory patient a physician or trained nurse can attend is the person who is habitually endeavoring to commit suicide. The most unsatisfactory appliance one can select for practical utility is one that will, unless watched carefully, destroy itself. People are beginning to realize that the Edison storage battery is a robust, normal, well-balanced affair, ready and willing to perform useful service day and night, and with all idea of self-destruction left out of its composition. Why? Because it is the only true storage battery ever conceived. The only battery, the elements of which are not attacked by the solution in which they are submerged, when left standing in a charged or discharged condition for an indefinite period. Steel is preserved by potash. So also are nickel and iron oxide. The Edison storage battery is composed entirely of nickel, iron oxide, and steel submerged in a solution of potash. That is the reason it lasts and does not deteriorate in use or out of use. When the late Lord Kelvin returned to Europe after making his last visit to America about 12 years ago, I had the good fortune of being a fellow passenger. I was engaged at the time in perfecting an electrical instrument I had invented to enable the deaf to hear, and in which, owing to his defective hearing, he was much interested. He asked for a detailed explanation and demonstration of the instrument. With due respect for his superior knowledge, I was dwelling only on the most important features. He interrupted me. "Stop! Start at the beginning. Assume I know nothing. Then I will not miss anything. Tell me what to look for, and then demonstrate." In explaining the Edison storage battery to you, I am going to take the liberty of assuming you are not familiar with the subject. I will start at the beginning, tell you what to look for, and then demonstrate. A storage battery is commonly looked upon as a receptacle in which to store electricity. Electricity is not concrete matter. In fact, nobody knows just what it is. Therefore, in the general comprehension of the term, it is not stored. Electricity simply causes a chemical change to be effected in certain substances when it is caused to flow through them. These substances, in endeavoring to return to their original state, produce electricity. Suppose we place two pieces of very thin, bright steel out of doors for a few weeks. They become rusted. The action of the oxygen on the outer layer of the metal has formed it into an oxide, commonly known as rust. Now let us place these two pieces of steel into a solution composed of potash and water and connect them by wires to a small dynamo. The electricity flowing from the dynamo through the solution from one of the plates to the other and back to the dynamo changes the rust to metallic iron on one of the plates, but causes the other plate to become rusted twice as much as before. Now let us disconnect the plates from the dynamo and connect them by means of pieces of wire to an ohmmeter, an instrument for measuring electricity. Instantly the pieces Instantly, the excess oxygen in the rust on the one plate commences to pass back to the bright plate, and by so doing causes electricity to be generated. Why? Nobody really knows. We have now charged and discharged a primitive storage battery. Instead of two thin rusted steel plates, let us mount, say, 100 such plates, equidistantly spaced on one rod, and 100 more on another rod. Now suppose we interpose the two groups so the plates of the two groups will not touch each other, and then connect them to our dynamo. The electricity will flow from one group through the solution to the other group, converting the oxide of one group to metallic iron and increasing the amount of oxide on the other group. We will be able to get much more electricity from the battery thus formed because of the greater plate surface exposed. We have thus determined that large surface is necessary. Let us next place a lot of fine particles of iron rust into two perforated flat steel pockets, and after putting these pockets into potash solution, pass electricity from one to the other through the solution as before. All the iron rust in one pocket will be changed to metallic iron because the oxygen will have passed over to the iron rust in the other pocket, causing this material to possess twice as much oxygen as before. The superoxidized pocket tends to swell to a cylindrical shape. Now when you connect the two pockets to your ohmmeter, you will find that much more electricity is flowing than before, although the two pockets take up much less space than the 200 steel plates. The reason of this is the small particles present a very great continued combined surface to the solution. Suppose after having made a great number of experiments, you find if you put some iron oxide into perforated steel pockets and mount a lot of these pockets on a steel grid or support to form one plate, and place nickel hydrate, a green powder, into perforated steel tubes, and mount these tubes on another steel grid to form another plate. You will have arrived at the point Mr. Edison reached when he discovered the Edison storage battery. The electricity flowing through the solution from the tube or positive plate to the pocket or negative plate causes the oxygen and the iron oxide of the pockets to come over to the green nickel hydrate. This oxidizes the hydrate and forms a new kind of nickel oxide, heretofore unknown chemically. This oxidizing of the hydrate tends to cause the tubes to swell, but they are already round, cylindrical, and are furthermore reinforced by a number of steel seamless rings placed around them. It is therefore apparent that they cannot swell. We continue to pass the current through until the iron oxide in the pockets has been converted to metallic iron, and the green nickel hydrate in the tubes becomes a very black nickel oxide. Then when we connect the two plates to our ohmmeter, the improvement will be apparent. At this point, we will still find, however, there is room for improvement, just as Mr. Edison found. Some substances permit more light to pass through them than do other substances. Likewise, some substances present greater resistance to the passage of electricity through them than do other substances. This nickel oxide in the positive plates has high electrical resistance, so it becomes necessary to divide it up into very thin layers and to conduct the electricity to these layers by intervening layers of metal. I will explain to you how I will explain to you later how this was accomplished. It was exceedingly difficult to achieve and cost Mr. Edison much money and effort. Figure 1 shows one of these negative plate pockets containing iron oxide. Figure 1 pocket for negative plate. Figure 2 illustrates one of the perforated steel tubes reinforced by equidistantly spaced steel seamless rings. Figure 2 positive plate tube. Figure 3 gives one a very clear conception of the appearance of the negative plate, on which 24 of these pockets have been secured. Figure 3 negative plate. So 8, 16, 24. Figure 4 shows 30 of these steel perforated tubes mounted on their steel grid, making up one of the positive plates. So there's 15 and 15. So the positive plates are tubular, the negative plates are rectangular components. The loading of the tubes is accomplished by an automatic machine operating as follows. After the perforated steel tubes have been made, they are placed vertically into iron clamps directly under a row of fixed tubes through which metal rods pass. After a little metal cap has been inserted into each of the tubes, the machine is put into operation, and a very small quantity of green nickel hydrate, the green powder, is allowed to fall into the tubes. On top of this falls, in an evenly distributed layer, some very finely divided metallic nickel scales. The metal rod descends and, under a pressure of about 2,000 pounds to the square inch, forces this thin layer of nickel scales into very intimate contact with the thin layer of nickel hydrate. The rods are raised and the performance repeated until a total of 700 alternate layers of nickel hydrate and flake nickel have been tamped together. Besides making intimate contact with the successive layers of nickel oxide, the layers of nickel flake make the contact with the sides of the tubes, so that when the tube is placed into a solution of potash and water, the charging current passes to these layers of flake nickel and through the thin layers of nickel hydrate for the purpose explained. After the tubes have been filled, they are removed from the iron clamps. Another metal cap is inserted in the top of each, and the two ends are mashed flat as shown in Figure 2. The tube is then placed into a machine which forces the seamless steel rings over it, equidistantly spacing them. 30 of the tubes are then mounted on grids shown in Figure 4 and firmly clamped thereto by means of retaining ears forming part of the grid. The negative pockets shown in Figure 1 are formed into halves, open at the top. These pockets are clamped in a device and loaded with iron oxide by machines similar to the tube loading machines, although it is not necessary to interpose layers of metallic nickel flake because iron oxide has lower resistance than the nickel oxide in the positive tube. The conductivity of the iron oxide is increased by mixing with it a little mercury oxide, which is all sufficient. 24 of these pockets are placed into interstices of a steel grid and subjected to hydraulic pressure, which firmly clamps them to the grid. It also corrugates the sides of the pockets, imparting to the said sides sufficient elasticity to cause them to always adhere tightly to the iron oxide mass within. We come now to the assembly of these positive plates and negative plates to form a battery. For convenience, we will mount 4 of our positive plates on a steel rod, for the plates being equidistantly spaced by means of steel washers fitting over the rods and between the plates. We similarly mount 5 negative plates on such a rod. 2 nuts at the ends of each of these rods, when tightened, firmly clamp the plates. Figure 5. Type A4 cell assembled but entirely removed from container. Figure 6. Top of A4 Edison cell. Filling aperture and check valve open for adding distilled water. We now sandwich the 4 positives and 5 negatives together as shown in Figure 5, so that between the negative plates, positive plates are interposed. It becomes necessary to keep these plates from touching. We therefore place a number of hard rubber rods between them. The crevice formed between adjoining tubes of the positive plates providing a channel to hold the little rods in position. We then fit the hard rubber ladder pieces to the edges of the plates. The cross members of these ladders have little grooves so that the edges of the positive and negative plates fit into them as a drawer fits into a table. This keeps their edges apart. There must be a receptacle into which to place a combination of plates so nested together. The can, as this container is called, is made up of sheet steel, all steams of which are welded by means of the oxygen acetylene blowpipe. The sides of the can are corrugated to provide mechanical strength and radiating surface. The hard rubber bottom support shown at the bottom of plates, Figure 5, is placed into the steel can. The nested plates are slipped in with their hard rubber ladders in place. 2 thin sheets of hard rubber are slipped in between the sides of the can and the outside negative plates, and the entire unit is ready for the top. After the 2 hard rubber washers have been placed over the vertical pull pieces shown in Figure 5, the top is put in position and likewise welded to the can. Please note that the top is welded on. Pretty good indication that we do not expect to have to get into the Edison cell again. The fittings through which the vertical pulls or terminals pass are provided with soft rubber washers and means for expanding these soft rubber washers to form gas tight and liquid tight joint between the top of the can and the poles. Mounted on the top of the cell is an aperture through which the solution can be put into the cell originally, and also which the solution is replenished with distilled water from time to time, as will be explained later. The top of this aperture, the part that is shown open, is a little valve which allows the gas generated within the cell when it is being charged to get out of the cell, but which prevents any exterior impurities, air, etc., from getting into the cell. After the solution, consisting of potash, distilled water, and a small amount of lithium, is put into the cell, it is placed on charge and discharge successively for three complete cycles, after which it is ready for shipment. The mechanical parts of the Edison storage battery are composed of the highest grade of steel throughout. These steel parts are heavily nickel-plated, after which they are placed in retorts hermetically sealed and hydrogen gas fed thereinto. The retorts are placed in a furnace and brought up to the proper heat, at which the nickel becomes firmly welded to the surface of the steel. This forms an impervious preserving coating of nickel for the exterior of the cell and provides excellent electrical contact of all the parts. This process is one of the many that had to be invented and perfected for the manufacture of the Edison storage battery. Figure 7. 4 A4 cells in tray complete. One cell has filler cap open to show construction. Right there. The last one there. The cells are mounted in trays in the manner shown in Figure 7. These trays are of wood, having attached thereto metal cradles for holding the cells and metal clamps on top for securing them in place. The electrical connections between the cells are then completed, the positive pole of one being connected to the negative pole of the next, and so on. These connections fit over the tapered poles or terminals of the cells, and are brought into intimate contact therewith by the nuts of the rod. These connections fit over the tapered poles or terminals of the cells, and are brought into intimate contact therewith by the nuts on the ends of the poles. Therefore, to remove a cell from a tray, or to disconnect one cell from the other, it is only necessary to remove the nuts and, by means of a little jack we provide, pull the connection off the pole. There is no lead burning necessary as obtains with other storage batteries. So we'll go to letter 3 on the next video, and my battery's almost out on this little Samsung S3, but I want to show you something real quick. So the original Edison battery terminal pullers are pretty much unobtainium. You might find one randomly, but years and years of looking and waiting around got me impatient. I went and got this Craftsman battery terminal puller. And for some reason, it's not showing up very good. There we go. It's not showing up very good. Battery terminal puller. Really cool. If it would show up, the graphics and stuff. Really interesting. Comes in a wax box. You don't see that anymore, except with produce. Anyway, it's the best you could probably get. This is probably close to what you would use to get some of those terminals up. And I've used this a little bit I can't remember specifically on what right now, but that's an idea of what a battery. Probably not the Edison one looked like this, but it was probably close. And the idea is you create torque, and then that wedges the two components apart. So anyway, so that's the end of this video. Hope you enjoyed it. Oh, now it's coming up. You can see the graphics are pretty cool. This is obviously for a car battery, but like a lead battery, but physics are about the same. So anyway, thought you enjoy that. So we'll continue in the next upload, and make sure you can find my channel again if you want to see the other chapters. You know what to do.